This is a reminder that you should feel free to take as much time as you need to write all of the notes down and think about them. Pause the video at your own pace. Welcome everybody to section 4.6, day 2, division of polynomials. We learned how to do a whole lot of division in the last section, and you might say, so what, Bergman? Who cares about this division? When are we ever going to use it? Well, we're going to use some applications. These are all basically the applications of division today. Let's start off with the remainder theorem. Basically, what we're saying is you can rewrite any function as f of x is equal to x minus some c value times q of x, that would be the divisor, plus the remainder. So if you're substituting a value in for c, let's say c is equal to 3, it would be x minus 3. F of 3 would make all of this equal to 0, because this is x minus 3. This would cancel out. And then you're just left with the remainder. F of c is equal to r. F of 3 would be the remainder. What you're basically saying is that if you want to substitute a number like 10 into a function, then maybe substituting in would be kind of difficult to compute. But an easier way to do that would be to use synthetic division to find the remainder instead of flat out just plugging in all the numbers and calculating that by hand. Maybe it's easier to find the remainder. So what you could do is you could say, you take all the coefficients, here are the coefficients 2, negative 3, 1, negative 2, 10, and you, 10x, and then negative 8 is the last one. And then you take all the coefficients anyway, and then you use synthetic division with 10, the number that you're substituting. So bring down the 2, multiply by the 0, add, 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 multiply by the 0, and you get the remainder of 168,802. The book suggests that maybe this is a bit easier. So you could say that f of 10 is what the remainder is here, 168,802. Determine whether 5 is the 0 of g of x. Well, you could substitute it in as a value and see if you get a remainder of 0. So 5 is the potential 0. Let's take 5 and plug it into, 1. There's actually no x cubic term, so we have to insert a 0. Minus 26. There's no linear term, so we have to insert a 0, and 25. If 5 is a 0, we should be able to substitute it in and get 0 out. So we bring down the 1, multiply by the 0, add, 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 and we get 0. So is 5 a 0 of g of x? Yes, it is. It produces no remainder. Determine whether the imaginary number I is a 0 of f of x. This synthetic substitution works along the complex numbers also. Check it out. It's the same process. Don't freeze up just because you see an imaginary number. The process is still the same. You line up all the coefficients, bring down the 1, multiply by the 0, add, multiply by the 0, negative 3 plus I times I would give you negative 1 minus 3I, add, multiply by the 0, add. So yes, I is a 0 of f of x. The process works for complex numbers also. The factor theorem. For a polynomial f of x, if f of c is equal to 0, then x minus c is a factor of x. So if you can divide, if it's a 0, if c is a 0, then x minus c is a factor of f of x. So, for example, let's use the factor theorem and I'll show you how it works. If f of x is equal to x cubed minus 3x squared minus 6x plus 8, then we want to factor f of x and solve the equation. How do we factor it? Well, maybe one of the best ways to do it is just to guess. we're going to guess numbers that could be zeros of the function. Let's guess 2. Why not? 2 is here, and we have 1. So we line up all of the coefficients. We add, multiply by the 0, add, multiply by the 0, add, multiply by the 0, add, we get a remainder. Because we get a remainder, then 2 is not going to be a 0 of the function. It's not going to be, and then x minus 2 is not going to be one of the factors. We're going to have to guess again. Let's guess 1. If we have 1 here, then we're going to bring the coefficient, bring down the, write out all the coefficients, bring down the 1, multiply by the 0, add, multiply by the 0, add, multiply by the 0, add, we get a remainder of 0. Yay! So therefore, we can say that this 1 is a 0 of the function, and therefore x minus 1 is a factor. We're using the factor theorem. If it's a 0, then x minus that 0 is a factor. And there it is, x minus 1. Translating the result here that we get, x squared minus 2x minus 8. So now we took it one factor out, and then this is actually a lot easier. Once we get to quadratic, we have tons of tools for factoring quadratic expressions. And there it is. So therefore, the zeros are going to be positive 1, positive 4, and I want you to tell me what the third 0 is. Connecting the concepts, here's a nice big chart that connects everything all together, wraps it all up in a little bow. Consider this function, or this polynomial function. These are the same functions. This is the factored form, this is polynomial form. And its graph right here. You can say the following things. Negative 3 is a 0 of f. That means f of 3. Negative 3 is a 0 of f. That's the same thing as saying f of negative 3 is equal to 0. That's the same thing also of saying that negative 3 is a solution of the polynomial equation right here. It's the solution of these equations when you set it equal to 0. Negative 3 comma 0 is an x-intercept of the graph of f. So zeros are the same thing as solutions, the same thing as intercepts, x-intercepts. We can also say that 0 is the remainder when f of x is divided by x plus 3, or x, really it's x minus negative 3. Andrew Jackson learned how to do this when he was president. He was doing this all the time when he learned, when he was taking his Algebra 2, and you can too, just like your presidential audio check fact, Andrew Jackson. And then you can also say, because of the factor theorem, you can say x minus negative 3, or just simplified x plus 3, is a factor of f, the function f here. And so you can say all of these things, they're all related, and they're all connected, all concepts that are connected to each other. And you can make similar statements for negative 1 and for positive 2. I'd like you right now to start your assignment for F2, copy the problem list, do the first problem, and I will see you in class.